Dear students, today I am going to begin with the first topic, that is the pharmacodynamics, and in the second part I will discuss the pharmacodynamics and its concepts. If you remember the first class where I have introduced you with the terms like what are the pharmacokinetics and what are the pharmacodynamics, and various other introductions of pharmacology and that we have discussed on that day. So today pharmacodynamics will take in little detail. You can see the first slide where you can find some structures. These are structures of proteins, and which are ultimately giving you various structures, and these all structures are needed for the pharmacodynamic process. So there's a huge role of the various proteins in various forms, in various names, and in various ways, and then this whole pharmacodynamic process actually happens. So let's see what are these pharmacodynamical concepts, pharmacodynamics. Now I thought to begin this chapter first with the questions, so you will get an idea that what actually is going to come on your way, right? So these kind of questions are very common in the examinations as well. So just listen the questions carefully, because once we'll move into the next slides or other slides, you will keep on getting the answers of each of them. So first is define pharmacodynamics. So what is the definition of the pharmacodynamics? I have given it earlier, but here again I have given once, so you can go through in the coming slides. Question number 2, define the terms like what is agonist, what is inverse agonist, what is antagonist, ligand, affinity, intrinsic activity, and receptors. Another question is classify the probable actions of any drug. So this question is asking you, just consider any drug. If it goes into the body, it will produce some actions. So what are those possible actions that we have to define? Another question is give the example of drugs producing its effect through its physical form, right? So there may be drugs, their physical form is such which is actually producing some effects. So physical form, their adsorptive property, their osmotic activity, their radioactivity, and oxidizing property. So we'll get to know. Next question is to discuss the possible targets of a drug action. So once if the drug has to produce its action, where it will produce, or what are those targets for the drug action, so that we will see. Explain the enzymatic drug action with example. So here if there is an enzyme, so what is that enzymatic drug action that we need to know. So these are some possible questions under this topic. Let's find out the answers. This is one diagram, just a kind of overview. You can see the first phase, I'm showing you the pharmacokinetic. So this portion is the pharmacokinetic. Already this part you have covered. You know very well that how the drug absorbs into the body, and after the absorption where it reaches to plasma, and from the plasma what happens, it goes to the various locations in the body, which we call it as distribution. Then from there it reaches to it get metabolized, and same time it produces its effect, and then it excreted out from the body. So this is what you have seen in the case of the pharmacokinetic. But from here if you see from here to here, you can see this is the whole process of the pharmacodynamics. That what we will discuss in the coming lectures. So here I'll just tell you a little course information about it. Once the drug which goes into the body and reaches to where it has to produce its effect, there it may get bind with certain proteins which you are calling as a receptors, right. So every time all the drugs are not producing its effect by binding with the receptors, but here just for your understanding, it's given that drug is binding to its receptor, and once drug binds with the receptor, it makes a complex, right. So it will become a drug and the target complex, and that complex will further, activate the biosignal flux which is happening by means this complex will act on certain factors or the chemicals which are present in your body or various proteins. Most of the time they are proteins. So they bind with those proteins, and then effect may produce, right. So this effect is not directly produces, while it may go and bind with the nucleus, and in the nucleus it go and bind with the what called the genes, and then so this whole process actually, right, the complex activates some protein, then some protein will activate other protein, the other protein will activate other protein, like that it moves on. So it's a kind of a pathway, right. So here it's called a signaling pathway. So by that ultimately you will get the efficacy or the effect of a drug, right. Same time, if the effect will go in the little exaggerated form, then the toxicity can also be observed. So this is the one simple pathway which shows that how a drug enters, and then after completing the pharmacokinetic or together, actually there is no separate process like once this happened and then that happened. This categorization is only in the book, but it is not in the body. So all the processes are happening together. So like that the drug can achieve this effect, or you will get effect from the drug by passing all these phases. So pharmacodynamics, if you want to define again the action of a drug on the body. So one thing is pretty clear, that the action of a drug on the body, in the kinetics you have seen that the action of the body on the drug, right. So when drug reaches into the body, what body does with the drug, right. So that was the process. Now what the drug is going to do, because you have taken the drug for a purpose, so now what the drug is going to do to your body. So that is pharmacodynamics, including the receptor interaction. So what are the components in the pharmacodynamics will come? Receptor interactions, dose response phenomena, right. How much dose and how much response will come, that relationship. Mechanism of therapeutics and drug action, how a drug gives its effect, so that mechanism we have to find out. So this all factor comes together in the pharmacodynamics, right. So most drugs act by associating with the specific macromolecules. So here we are using the term macromolecule. Macromolecules are the proteinaceous molecules. Later you will name them receptors or other transporters and other many things. So once the drug binds with the associates with the macromolecules, they alter the macromolecules. Alter means they change their structure, or some changes will happen into that macromolecule, right. Then what will happen when the changes comes? Biochemical or biophysical responses will be there, right. So like that these all things comes under the pharmacodynamics. Now what happens in this particular case, here just example is there. Suppose that there is a drug, we call it as D, drug D, and there is a one receptor or effector which we call it as R. So once this drug go and binds with the receptor, it forms the drug receptor effector complex, right. And when the complex forms, the effect happens. You have seen in the previous diagram, right. So these are some combinations have been shown that the different drugs follows the different methods of producing its effect, right. There are in some drugs they are having more molecular pathways, right. There they go for the coupling activation of coupling molecules, like that one whole process or one whole pathway they follow. Okay. Here you can see just one simple diagram which tells the drug. These are this side, these all has been shown like these are the drugs, these are the drugs, and this is your receptor. So what happens, suppose that this is the receptor and these are the binding sites, these are called the binding sites, right. So different binding sites have the different structure. So these different structures of the different binding sites, you see the agonist. So agonist has the structure which can nicely fit into the groove or nicely fit into the binding site which is given. That's what the drugs which are nicely fit into the structure and producing the effect. So we call it this agonist. Same way there is another inhibitors maybe which we call it as competitive inhibitors. They have a little different structure but can fit into this groove. So they can inhibit the effect of the agonist, right. The next one is the allosteric activator. These activators are not binding to the same active site where the agonist and competitive inhibitors are binding, while they act on the different sites other than the active sites, and then they have the capability to produce some changes into the structure, right. So the same way allosteric inhibitors are also there, which are not binding on the allosteric sites but on the different sites, and producing and changing the overall structure of the protein, and then this way they alter the drugs effect. So this is one understanding. Now every drug, whenever it goes into the body, every drug has to produce some action. That's what the objective behind every drug. So drug has to produce some drug action. So what is the drug action? How you can define the drug action? So it is the initial combination of the drug with its receptor, resulting in a conformational changes in the later, right. So what happens when a drug binds to a receptor, it produces the changes in the receptor structure, okay, and these changes we call it as conformational changes. Means these changes are confirmed, means some confirmed changes happen, because these confirmed changes can only bring the change in the effect or change in the process, or you can say initiate a process, right. That is only possible when conformational changes happens, okay. So usually who brings this kind of conformational changes? Agonists, okay. Later I will explain you, define the agonists, then you will understand. Or prevention of conformational changes. Maybe there are certain drugs which not causing the conformational changes, but they are preventing other agents or other chemicals to cause these conformational changes, right. So we call them as an antagonist. So this way the drug action happens. Now if we talk about the drug actions, let's see how many type of these possible drug actions are there, right. So possible drug actions, for example, first drug action, or a drug, when you take a drug will do something, right. So what drug can do, right. What are the possibilities that a drug can do? So one thing, the first possibility is that the drug can stimulate something. The drug can stimulate some process, drug can stimulate some cell, some organ, some system, right. Something it will stimulate, right. So that's why we call it as a selective enhancement, right? So in a particular part, in a particular thing, particular enzyme, particular factor, particular chemical, right, that will get enhanced its activity by the stimulation. For example, adrenaline is a drug, increases the heart rate. So it is what the adrenaline is doing, adrenaline is stimulating the heart. Okay. Same way, if you take the drug pilocarpine, so what the pilocarpine drug does, it stimulates the salivary gland. Okay. So this way various drugs are there, those who are doing the various type of stimulations. Now if the drug is not stimulating, then what a drug can do? Then drug have another choice, that drug can depress something. Okay. So drug is going to depress something. This is called selective diminution. So drug will go and suppress or diminish the activity of something. Okay. For example, barbiturates, here is written wrongly, it's not stimulates, it depresses the CNS. And same way quinidine, which is also depresses here, quinidine which is also depresses the heart. So this is some copy paste error from the previous one. So don't confuse, barbiturates depresses CNS, quinidine depresses heart. Okay. Next, what a drug can do? Drug can produce the toxicity in a cell, or you can say the drug can cause a cell death. Okay. So that also drug can do. Usually these cytotoxic actions comes when you are discussing about the adverse effect of the drugs, toxic effect of the drugs. There we are discussing about the, but that is also either its adverse effect or a toxic effect, that is also a drug action. Okay. So we'll see here what this is doing, utilized for cure or palliation of infections and neoplasm. So generally the area which are infected, so infected by the cells may be microbes, so there are drugs which are killing them, so it means they are killing a cell. And in case of the neoplasm, means cancers or tumors where the tumor cells need to be killed, so ultimately you need the cytotoxic drug. So these are the cytotoxic effect they are producing. For example, penicillin, chloroquine, zidovudine, cyclophosphamide, and so many other antimicrobial drugs are there, as well as anti-cancer drugs are there in this category. Another thing what a drug can do, that is a irritation, that drug can irritate certain system, right? For example, mild irritation may stimulate associated functions. So what is happening, whenever there is a mild irritation, the mild irritation stimulates something. So that's why certain drugs are used as an irritants. Example, bitters. Bitters are the category of drugs. So they are named bitters because they are actually taste as bitters. Increases salivary and gastric secretions. If you take some bitters, right, they will increase the salivary and gastric secretion. You can see in case of chili. So what it does, it causes some irritation, and by that you will get your gastric juice secretions, right? So same way all these spices also do these kind of job. So there are drugs also who which are doing the similar thing. So example, bitters increases salivary and gastric secretions. Counter irritants increases blood flow to the site. So this way they do. One more effect what the drug, one more action what the drugs are producing, replacement, right? So there are certain factors which are doing something, some chemicals which are doing some work. So what these drugs are doing, they go inside and replace them, right? So for example, in case of the hormones, usually we do. So use of natural metabolites, hormones, or their congeners in deficiency states. Example, levodopa in Parkinsonism, insulin in diabetes mellitus, iron in anemia, right? So you know that insulin is producing in your body and controlling the diabetes condition. But when insulin is not sufficiently producing, you are giving insulin from outside as a drug. So that drug goes and replaces that insulin effect and produces its own effect. So like that, these are the possible actions what drugs are producing. Now we'll see, you understood these are the actions what the drug is doing. Now how these actions are drug. So how drugs act. Uh, Before we go in the molecular part of the drug's effect, first we'll see there are drugs which are producing their effect or because of their physical or chemical properties. So which are these drugs, right? So for example, drugs which are producing their effect by their physical mass, right? Their physical mass is being used for producing certain effects. For example, bulk laxatives, isabgola. You know the isabgol and the bulk laxatives, what they do when they go inside and they utilize the water and they get swell up and they help in the motion and defecation. So like that they are producing their effect by their physical mass. Physical form, there are drugs which are producing their effect by physical form like opacity, right? So dimethicone, petroleum jelly has been used. Absorption of UV rays, para-aminobenzoic acid. Adsorptive property, activated charcoal. You nowadays you might have seen the face washes with the charcoal, toothpaste with the charcoal, some face masks with the charcoal, and so many things. So what the charcoal does, charcoal is having adsorptive property, so it adsorbs in it certain things, right? So that's called the activated charcoal. Osmotic activity, example mannitol, magnesium sulfate, they produce their effect by their osmotic activity. Radioactivity, that iodine 131 and other radioisotopes. Neutralization of gastric HCl, you know very well what the antacids does. So because of their physical form, they are neutralizing the gastric acid. Oxidizing property, there are drugs which have their oxidizing property. Some drugs producing their effect by chelation of heavy metals. For example, EDTA and dimercaprol. Sequestration of cholesterol in the gut, cholestyramine, they are the very good anti-cholesterol drugs. So like these various drugs which are producing their effect not by binding to the receptors or other things, just by their physical form. So these are the effects by their physical form. Now we'll see some very important definitions and I expect that you all should remember these. What is the agonist? What we call the agonist, right? Listen it carefully and remember it. Agonists are those agents which activates a receptor to produce an effect similar to that of physiological signal molecule, which has both intrinsic activity and affinity. So here any agent which is going to bind with the receptor, right? So this agent can be your drug. This agent can be any indigenous body substance. So and another thing is once they bind to the receptor, they activate the receptor, and after activation some physiological responses will be produced, right? So in this way you can say that first thing what this agonist has done, it has some binding activity or binding nature with the receptor. So affinity always have agonist always have a affinity. Affinity means a binding nature, a binding approach towards the receptor. So first thing, it must bind with it. So once it bind with it, we call it as it has affinity. After binding, if it is able to produce certain effect, that ability we call it as intrinsic activity. Okay, so agonist, always keep in mind that agonists have intrinsic activity and affinity, both. It has both affinity as well as intrinsic activity, right? And by that it can bind with the receptor and activate it, and it produces the responses. So this is what we call agonist. Another term is that called inverse agonist. Inverse agonist means an agent which activates the receptor to produce an effect in the opposite direction to that of the agonist. So, inverse agonist is the one which is having the similar activity like agonist, but it will produce the effect in opposite directions. And next is the antagonist. Antagonists are those agents which are having the opposite effects as the agonists, and they are binding with the same site where the agonist binds, and in this way they are inhibiting the agonist to bind with it and to produce their effect. So they have the affinity to bind with, but because they bind and no effect comes after that, so they have no intrinsic activity. So keep remember that the antagonists have the affinity but they have no intrinsic activity, while the agonists have the affinity plus intrinsic activity. Okay. Another term is the partial agonist, in which these agents which activates a receptor to produce submaximal effect, means they are binding on the same site where the agonist have bind, but not binding properly. So because when they're not binding properly, the effect is not being produced optimum. So they have a substandard or sub maximal effect produces. In that term, the you can say the effect is not proper. Another term is called ligand. Ligand means any molecule which attaches selectively to a particular receptor or site indicates affinity. So what does it mean, ligand? Anything. This is another term, a general term, means anything. It can be agonist, it can be antagonist, it can be any other thing which binds on the receptor, we call it as a ligand, right? So anything which is binding on the receptor called as ligand. So it means these agents are having one thing for sure, that is the affinity. So now we'll see in detail the targets of these drugs action. So I have told you in beginning that every time when you are discussing about the pharmacokinetics, you are discussing a lot about the proteins, because so many proteins are going to play very important roles in the process of the pharmacodynamics, and everything which comes on the way for the pharmacodynamic process, most of them belongs to the proteins, right? So these proteins comes in different forms, different structures, different way they bind with it, right? So for example, these category of targets are enzymes, ion channels, transporters and receptors, and if you see, all of them are made up of proteins. So first we'll discuss about the first target, which is called the enzyme. You already have good knowledge of enzyme as you studied in the biochemistry first year. So this will help you out to link with that and understand in a better way. So enzymes, the drugs can either increase or decrease the rate of enzymatically mediated reactions. In our body, there are so many reactions are going on which are mediated by the enzyme. So suppose that you want to activate certain enzymatic reaction, or you want to stop certain enzymatic reactions, right? In both the way you have to target that particular enzyme to stimulate or to inhibit, right? So let's see what these enzymes are doing. So first method is the drug can stimulate the enzyme. So if the drug is stimulating the enzyme, we call it as enzyme stimulation. Several enzymes are stimulated through receptors and second messengers. So sometimes what happens, these enzymes are stimulated not directly by the drug, but the drug activates the receptors and these receptors activate the enzyme. Same way, sometimes the drug activates the receptor, then receptor activates the second messenger. Second messenger means after the receptor, the next protein which is going to get activated and to convey the message further through the another protein, we call it as a second messenger. So the another protein which has been conveyed by the second messenger called as third messenger. So like that the whole process moves on. So in this process, what is happening here in enzyme stimulation, examples have been given here. Adrenaline stimulates hepatic glycogen phosphorylase through the beta receptor and cyclic AMP. So here I'll just make you understand this process. Adrenaline stimulates hepatic glycogen phosphorylase. So adrenaline is your drug. So I'll write adrenaline. So adrenaline is your drug, right? So this adrenaline is going to bind with which receptor? Beta receptor. So we'll write here beta receptor. So adrenaline is your drug, beta is your receptor. So adrenaline has bind with the beta receptor and made a one drug receptor complex, right? Once this complex has been formed, this complex will activate other protein. That protein can be your second messenger, and in the case here the second messenger is cyclic AMP, right? Cyclic AMP. Now adrenaline has bind with the beta receptor, and this complex has activated a CAMP, which is a second messenger, and this CAMP can do the activation of glycogen phosphorylase enzyme. So it's the activation of glycogen phosphorylase enzyme which is present in the liver. So this way a drug adrenaline has done the activation of glycogen phosphorylase enzyme, but not directly, but through receptor. It has done the process through receptor, you can see here. So adrenaline has done the activation of this particular enzyme through a receptor, right? So this is called the enzyme stimulation. Same way, if a drug which is not stimulating the enzyme, so what it can do? It can inhibit the enzyme, means inhibit the enzyme stimulation. Okay, so what will happen? The enzyme will not get stimulated. When enzyme will not get stimulated, enzyme won't do its effect, right? In the previous example, what you understood, when adrenaline binds with the beta receptor, it activates the phosphorylase enzyme, and the phosphorylase enzyme which is responsible for the phosphorylation in the glucose metabolism. Here, if you want to stop that process, so what you need to do, you should avoid or you should stop the activation of phosphorylase enzyme, and that can be done by inhibiting the binding between the adrenaline and beta receptors. So this way anyway, means this is one way. So there are other ways as well by which you can stop this activation. So if you are stopping that activation, called as enzyme inhibition. So there are huge huge number of examples available for the enzyme inhibitions. So these are of two type. Here we can see one is called non-specific inhibition. Non-specific inhibition means these drugs or agents which are the inhibitors, enzyme inhibitors, they are not targeting to a particular enzyme, while they can inhibit any other enzyme, any of the enzymes they can inhibit, right? For example, heavy metal salts, strong acids, alkalis, alcohol, formaldehyde, phenol, they can inhibit enzymes non-specifically, right? So any of the enzyme they can inhibit. They are not liable to inhibit a particular enzymes or a particular category of enzymes. And the second one is called the specific inhibition. In this case, the agents are going to inhibit the specific enzymes, right? So and when they inhibit the specific enzyme, they have to face the one condition. Once they are going to act on the specific enzyme, there already one agent which is called the indigenous agent or inherent agent which is available in your body. It's going to bind with that enzyme and to produce its stimulation. Okay, that's already there, but your drug which is an inhibitor, now it's going to stop that process. So how it happens? And in a general concept, you already know about it, that enzyme is going to bind with its substrate. substrate which is already present in the body. So, that substrate is going to bind with the enzyme, and then when the enzyme substrate binds together, they produce the product, right. So, here when you have given your drug is also going to bind with the enzyme, and in that case they are going to compete each other, means that agonist or that substrate which is already present and your drug, right, is going to compete for binding. Why they are going to compete for binding? Why not both can go and bind? Reason is that there is only one space available, there is only one active site available. So, they have to bind only onto that active site, and for that purpose they have to compete with each other, right. Now, in this competition one will win. Usually your drug has been designed in such a way that it will go in more concentration and it will bind first than the before the substrate do. So, your drug wins and it binds and stop the substrate to bind with it. So, the normal activation of enzyme will not happen, and there will be inhibition, right. So, here you can see in this example, you can understand very well that one substrate is there, one inhibitor is there. Inhibitor is your drug, substrate is the substrate which is available in the body, and now both are competing for binding in the same place in the enzyme. And if the substrate binds, it will forms the product. If the inhibitor binds, there will be no product, right. And there is a more chance that inhibitor will bind, because it has been designed in such a way to bind with it. And you can see the substrate and inhibitor both have the similar structure, and that's why they are both are able to bind with the enzyme. Now, the first method of the enzyme inhibition is the competitive inhibition, and in this competitive inhibition what happens, the drug which is an inhibitor and the substrate both are going to compete for the same site, and once your drug binds to that site, after some time that inhibitor will move from the active site and will leave the active site empty again. So, that is why they are again creating another equilibrium. Okay. So, we understand in this way the drug competes for the catalytic binding sites with substrate, so that the product is not formed or a non-functional product formed. Sometimes we can say when the inhibitor binding on the same site where the substrate is going to bind, then there will be no product formation, but sometimes the product forms, but that product is a faulty product or a wrong product, and the wrong product will not be accepted by the body for further action. So, the action will be seized off on that place. Okay. By this way new equilibrium will be developed. This is an example where agonist and competitive antagonist, you can see here the agonist and the competitive antagonist both are going to bind on the same site, which is the receptor site, and in other case you can find there is a one more site available here which is called the allosteric site, right. This is not the case of the competitive antagonism, you will see later. And here what is happening, here agonist in the below you can see the agonist is going to bind here, but the competitive antagonism has already taken the place. So, there is no place available for agonist to bind with it, right. Now, because the antagonist has affinity but no intrinsic activity, no response is produced, right. That you always keep in mind, that antagonist will never produce any effect, because antagonists do not have its own effect. Antagonist is only blocking the agonist effect. Such inhibitors increases the Km is the rate constant, and the Vmax is the velocity maximum of the reaction. So, if you see in this particular case competitive inhibition, the Km will increase while the Vmax will remain unchanged. In the next part of it, where we will discuss about the pharmacodynamic concepts, there you can understand these points in detail. These are the examples for the competitive inhibition. In the next chapters, all these drugs which are the examples here will be you will be studying in further classes. You see the examples physostigmine and neostigmine. both are the drugs of the cholinergic category, and they compete with the acetylcholine for cholinesterase enzyme. So, here acetylcholine is your substrate, cholinesterase is your enzyme, and physostigmine or the neostigmine is your inhibitors. Same way sulfonamide compete with PABA for bacterial folate synthesis. One thing I make it clear, above I said the physostigmine, neostigmine are inhibitors. They are not actually inhibitors, but they compete with the acetylcholine and bind on that particular place for cholinesterase, right. So, because cholinesterase is the one which inhibits the enzyme degradation, causes the degradation of acetylcholine. So, these are the drugs which are inhibiting this degradation, right. That will in the chapter cholinergic drugs, there we will discuss in detail. Another example of this is sulfonamide. Sulfonamide compete with PABA for bacterial folate synthetase. Captopril, which is an AC inhibitor, competes with the angiotensin 1 for angiotensin converting enzyme. Kindly remember all these examples, because whenever you are writing in the exam for this enzymatic inhibition, you have to write with examples. Okay. Finasteride competes with testosterone for 5-alpha reductase. Carbidopa and methyl-dopa compete with levodopa for dopa decarboxylase. So, these are all the examples. Here just one example given for partial agonist. You can see how the partial agonist binding with the same site where the agonist binds, but not properly, and because of improper binding it gives the submaximal response. Now, we will see the competitive inhibition, but the non-equilibrium type. So, what is the difference in this? Here what happens, the in case of non-equilibrium type, the antagonist or the inhibitor what you have is going to bind with the active site or with the same site where agonist has bind, but binds permanently. Permanently means either it will make a covalent bond with it and won't come out of it, right. So, it is a kind of loss of site will be there. So, that case there will be no new equilibrium will be developed. So, that is what we call it as an competition is there, but in the competition when your drug binds, it binds with permanently, that is called the non-equilibrium type. The examples are organophosphates react covalently with the steric site of enzyme cholinesterase. Methotrexate has 50,000 times higher affinity for dihydrofolate reductase than the normal substrate DHFA. In this situation, Km is increased and Vmax is reduced. So, just keep in mind. Now, we will move to the next condition, next type of inhibition, that is called non-competitive inhibition, right. So, you have seen in the competitive inhibition there was a equilibrium type and non-equilibrium type, and now we have non-competitive inhibition. In this there will be no competition between the two things, between the substrate and the drug, while what happens, your drug having another site to bind with it. So, drug is not binding to bind with the same site where the substrate is binding. So, there will be no competition and drug will bind on other side, but that other side is also quite capable to change the structure of the enzyme or active site. So, the agonist or the substrate will not be able to bind with it, right. So, the inhibitor reacts with an adjacent site and not with the catalytic site. So, keep in mind catalytic site means that active site. So, your inhibitor is not binding on the catalytic site, while it is binding on adjacent next site of that, right, but alters the enzyme in such a way that it does its catalytic property. The antagonist is chemically unrelated to the agonist, binds to a different allosteric site, altering the receptor in such a way that it is unable to combine with the agonist or unable to transduce the response. So, that is what they are doing, they are binding on other place and inhibiting. Because the agonist and the antagonist are combining with different sites, there is no competition between them. Even high agonist concentration is unable to reverse the block completely, right, because there is no competition, that is bind in different place, that is binds in different place. So, if there is a high concentration of the agonist also, it will not remove the antagonist from there. Thus, what happens here? The Km will be unchanged, the rate constant, and the Vmax will be reduced. Here are some examples, non-competitive inhibitors and enzymes. So, you can see acetazolamide binds on the non-competitive inhibitor for carbonic anhydrase enzyme, aspirin endomethacin, drugs are for cyclooxygenase enzyme, like that. These are the examples, read about it. Here you can see, that's what I was telling you. Here there is a one allosteric site is available. So, non-competitive antagonist comes and bind here. There is no competition for this particular site. Okay, but what it does, what happens? The non-competitive antagonist when binds here, it will alter. You can see it has altered the site. Because it has altered the site, so this agonist can't fit into it, and the process has been stopped. So, this is the way of acting here. So, you have understood about the first target of the drug action, that is the enzyme, and you understood how these drugs are acting on this enzyme by two methods, by stimulation and by inhibition, stimulation or by inhibition. So, inhibition, you have seen there are two methods, competitive and non-competitive. In competitive, you have seen they either they bind temporarily or they bind permanently, that they produce the equilibrium and non-equilibrium type, and in non-competitive there is no competition and the agonist binds on antagonist binds on the allosteric site and produce its effect, right. So, now we will move on to the next target for the drug, and the next target is also a very common target for the most of the drugs, that is ion channels. So, in our body a lot of movement of ions are happening. Because of the movement of ion, the cells get activated and do the transport processes are happening, activation processes are happening, signal transduction processes are happening. This all are happening because of the movement of ion, and they are using the channels. So, if your drugs are capable of changing the activation or deactivation process of the ion channels, then huge impact can be produced. So, what is happening here? You can see the diagram. Ion, this is an ion channel. Once it is blocked, or once it is open, in the open state, it is allowing the ion to cross through. So, proteins which act as an ion selective channels participate in transmembrane signaling and regulate intracellular ionic composition. So, they are also the proteins, as I told you other proteins, these are also the proteins, and these make them a common target for drug action. Drugs can affect ion channels either through specific receptors or by directly binding to the channel and affecting ion movement through it. What I want to tell you, that I explained you before also, sometimes the ion channels can be directly controlled by the drug or directly affected by the drug, and most of the time it's not happening. The ion channels are getting controlled by the receptors. So, means drug is not directly binding to ion channel, while the drug is binding to the receptor, and then receptor activates certain proteins, and these proteins will change the ion channel opening, right. So, like that they are acting. Examples of the various drugs which are acting on various ions, for example, local anesthetics which physically obstruct voltage sensitive sodium channels. Certain drugs modulate opening and closing of the channels. Example, quinidine blocks myocardial sodium channels. Nifedipine blocks L type of voltage sensitive calcium channels. Nicorandil opens ATP sensitive potassium channels. Sulfonylureas hypoglycemics inhibit pancreatic ATP sensitive potassium channels. Amiloride inhibits renal epithelial sodium channels. So, like that, these are the drugs, various drugs which are having their impact on various ion channels. Third target for the drugs is the transporters. You can see the diagram where a substrate binding with the transporter, and the transporter has taken that substrate and facilitate the transport from one side to other side. So, what these transporters do? Transporters have a huge role for the various indigenous processes in our body, and you can see that several substrates are translocated across membrane by binding to specific transporters, right. So, by these different transporters, they are moving from one place to other place. For example, if you want to see, you see the desperamine and cocaine, blocks the neuronal reuptake of noradrenaline by interacting with norepinephrine transporters. If you see, means what? The NET is the neuronal transporter which transports the noradrenaline, right? So what happens? The dopamine, desperamine and cocaine, they are blocking this NET. So if the NET will be blocked, then noradrenaline will not be transported. Okay. For example, we have some more examples here. For example, amphetamine, which blocks the dopamine reuptake by DAT, which is called dopamine transporter, right? So DAT will be blocked by amphetamine, so the dopamine reuptake will not be happening, and then the concentration of dopamine will be less in the brain. So like that, various transporters have been targeted and controlled by the various drugs. So just go through with the examples. These are very important examples, and all these drugs are producing the effects by acting through the transporters. Now we'll move to the last target for the drug action, which is called the receptors. This is the last, but from here that your real pharmacodynamic will start, because after introducing the receptors, in the next part of the pharmacodynamic class I will discuss in detail about the receptor concept, right? So receptor concept is one of the very important topic. For without this you will never be performing good in the pharmacology. So if you want to be a good pharmacologist, you have to be good in the receptor concept, that I will explain you in the next class. So now what are these receptors? Are the largest number of drugs do not bind directly to the effectors, that we know. Means what they are saying, that large number of drugs are not using the enzyme channels transporters as the target, but they use the receptors as their targets, right? So they bind on the receptors, and then these receptors will change their physiological actions. So these regulatory macromolecules, or the sites on them which bind and interact with the drug, are called receptors. So like that we call it receptor. Here you can see the example. One agonist is binding to the receptor, then receptor has activated the transducers. Transducers are the various proteins which are available, and these proteins will channelize this activation, and then finally they will activate the effector, right? So and the effect will be produced. Here you can see the various definitions have been given by various books about the receptors. I'll just read out one for you. A region of tissue or a molecule in a cell membrane which responds specifically to a particular neurotransmitter, hormone, antigen, or other substances. So various writers have explained it, the definition, in the various ways. Please go through these definitions, and at least you remember one definition, so you should know what the receptors are. So receptors are nothing, just a macromolecules which are allowing to bind something on them. When something binds on them, they will activate certain other proteins, and they in fact initiate a pathway of activation, or you can say the communication, and then the further action happens. Receptor, once you say in a common term, receptor means anything which receives, right? For example, if you go to airport to receive your friends or family, so you are the receptor because you have received them, right? So anyone who receives that, these are receptors. So here also one proteinaceous structure which is available either on the surface or inside of this cell, and is able to receive something and get bind with it, and initiates the further process of activation, called as the receptor. So like that the receptors can be defined. We'll have the huge detail of receptors later. So I hope you understood that the drug has various targets. These targets, I have explained how these targets have been used by the drug, and the last target was the receptor, where the receptors are various types and the various methods are there to act. That we will discuss in the coming classes. So if you want to read little more about these things what I have discussed right now, please use these reference books, and all these reference books are available with you. Please go through and keep me posted for the doubts if you have. This is assignment. Read the pharmacodynamics from the given reference books. So thank you for your patient and honest listening. I hope you have understood the basic concept of the pharmacodynamics, and as you have already understood the pharmacokinetical concept, so you know very well that how after the pharmacokinetic, how the drug is, how the pharmacodynamics is going to play the role, right? So pharmacodynamics is the one which gives you actually the molecular mechanism of any drug or any actions, right? So that we will discuss in coming lectures in detail, right? Thank you very much for listening this video.